This is, I think, the last slide out of this packet, and it's a problem. It's another probability combinatorics problem. You're getting a handle on these on your first two assignments, and maybe if you haven't tried assignment 2 yet, this would be a good warm-up for what you do on question 1. Okay, so just read the problem. 3 integers are selected at random and without replacement. Without replacement is a little bit redundant because selected sort of means that there's no replacement. It also means that there's no order to the things. Okay, so just a subset of 3 elements from the numbers 1 through 100. Anyway, what's the probability their sum is even? Okay, so like all of these probability problems where the distribution is uniform, it's just a matter of counting the number of possibilities. The sample space is, as usual for all these problems that have a selection, you're doing just a simple choose, so it's a set of all 3 element subsets. So the size of S is 100 choose 3. Okay, so E, the event that we want, is the event that the sum is even. How would you characterize the subsets that will give you an even sum? How would you count them? Okay, yeah, if you get 3 even numbers, the sum is even. Good, so all 3 are even. Is that the only case? Or 2 odd and 1 even. Good. Okay, and the other cases, 3 odd or 1 odd and 2 even will give you an odd sum. Yeah? Okay, so those are the 2 cases, and we sort of use the rule of sum. They're disjoint, right? So we're going to add the 2 probabilities together, or the 2 countings of these things. How many 3 even subsets are there? 50 choose 3, yeah. There's 50 even numbers, and we're taking 3 of those. And how many have 2 odd and 1 even? How'd you get that? Good, so 50 choose 1 for the evens, and 50 choose 2 for the odds. Okay, so you sort of have this and then quality to it using the rule of product. Okay, so the probability of this event occurring is the size of the event space divided by the size of the sample space, 50 choose 3 plus 50 choose 2 times 50 choose 1 divided by 100 choose 3. Now, I think it's important to realize that, sometimes, the numbers are too unmanageable that you can't do anything to them. And sometimes the numbers are small enough that you can do a little bit more, okay, that you might want to expand the chooses and see what you get. These numbers are small, okay, so in the context of the numbers, these are small numbers. And I think it's a good idea for us to unpack this and see what we get. The result might surprise you, actually. Okay, so 50 choose 3, if we get rid of the cancellation of 47 factorial, we're left with 50 times 49 times 48, 3 times 2 times 1. 50 choose 2 is likewise 50 times 49 over 2. I'll just dispense with the times 1. And 50 choose 1 is 50. The denominator is 100 times 99 times 98 over 3 times 2. Okay, and I want to not write a lot more. Okay, so we're going to do some cancellations of things. Okay, first thing we're going to do is there's a 50 as a common factor in the numerator here, and there's a 50 in this 100, so those 2 will go away. The 49s, likewise, 98 is 2 times 49, so those will cancel with 98, we get 2. And what else have we got here? This 3 times 2, if we flip that, we multiply everything on the numerator by 3 times 2, that will cancel these out. We'll also cancel this 2, but we need to put a 3 in there. Okay, so those go. And that's all that I see readily at hand. Hopefully I did that right. Okay, so this is 48 plus 50 times 3. And the denominator's got 2 times 99 times 2. And if we expand what's on the numerator, 48 plus 150 is 198. Which is exactly 2 times 99. It's kind of cool. And that's a half. It's exactly 50-50. That's really cool. Okay, it's exactly 50-50. Now, you might have thought of some other reason it might have been 50-50 maybe earlier on. Did you see any reason it might be 50-50 based on what you saw earlier on? Okay, there's only 4 things, and half of them are always even and half of them are always odd. I agree there's sort of a half and half going on here, and that's part of it, but it's not all the story. Right, so you're using the dice rolling argument from before. I agree with you in some regard. Once you select the next number, it's 50-50 whether it's going to be even or odd, except that you're not allowed to select the number you've already chosen, right? So it doesn't become 50-50 after you pick the first number. Yeah, but no, sorry, that's not it. Okay, one more and then I'll explain. Yep. Yeah. I mean, it's all sort of a combination of this. But if you look back at what might have made this thing odd, just think about the opposite case, the not case, the complement case. You might have all three being odd, which would be 50 choose 3. Or you might have one odd and two even. Okay? These are the exact same cases as the even case, and since they're equal, it must be 50%. Okay, so this is by symmetry with the complement case. Okay, and it doesn't work if you step it up to the next case of, what happens if you go to, 1 to 101. Okay, so you can't use symmetry in that case. And if you grind out the answer, you'll find that it's not 50-50. Anyway, it's going to be important, and you should always look for symmetry arguments whenever you can. Okay, so we saw an inductive argument that gave us a half before. This one is a symmetry argument, and that might simplify your expressions down in a hurry. Okay, cool. All right, so you guys are finishing up your second assignment this week, and we're going to move on to the next unit, which is on conditional probability today. I want to wrap up this unit by talking about a computer science application to the birthday paradox. I guess there were two of them, two versions. This is the one, or the generalization of the one that we did with 25 of you sitting here, eventually 30. If you have a randomized function where you have d things in the codomain, what's the chances that you get an injective function? Well, you don't get an injective function. I guess was the opposite. Okay, and this ended up being rather, I don't know, it's sort of fast growing, right? So we saw that the break-even point for 365 days a year was 23. Okay, to find any pair. Okay, so any pair. So this was the first matching birthdays thing, and the other one was this one, which I didn't exactly finish in its entirety, but we imagine there's one fixed birthday, your birthday, and then you keep on polling people until you encounter somebody with your birthday. Okay, so how many people are you going to poll before you're likely to get somebody? 50% ends up being when you take natural log of 2 of the number of days. Okay, so that's about 70%, and let's just write out how long this is going to take you, how many people you have to ask. So when n is around 365 times the natural log of 2, which is 253. Okay, so if you poll 253 people, you expect the probability of the event to be roughly 1/2. Okay, this is very different in character than the one. You're looking for a very specific pair. You're trying to match yourself. The other one is any pair. Okay, so you're looking for any pair. Okay, so these two problems relate to a lot of things in computer science. I'm going to show you a couple of them today. Okay, and it all has to do with these things called one-way functions. Okay, so or hash functions. Okay, and some of you have encountered hash tables before. If you haven't, that's no big deal. But it is a data structure that is sort of like a table, and it uses this application, this hash function, to sort of randomize things in a nice way. Okay, so what is a hash function? It basically randomizes your set of stuff, your set of data, your set of keys, by chopping it up in an indiscernible way. And this is much the way that you expect breakfast hash to be, right? It's easy to turn potatoes and corned beef and onions into hash, but it is not so easy to turn corned beef hash back into onions and potatoes. Okay, so once it's been chopped up, the idea is that it's really hard to figure out where it came from. Okay, and that's indeed all the useful hash functions, at least cryptographical hash functions, have that property that it is easy to compute. It's deterministic. It's not random, but it sort of behaves like a randomized thing. It'll give you a nice uniform distribution, hopefully, but you can't get the input back easily without brute forcing it. Okay, so those are the two properties. Let's just go through this. Okay, it's got to be deterministic. It can't have a random generator call in it because it has to be repeatable. It's easy to compute. It has a constant running time. And if you want it to be cryptographically viable, cryptographically secure, it can't be invertible. Okay, so this is the one-way function characteristic. Okay, and that is that the brute force solution is the only viable solution. You can't glean something from the way the mathematics works in the function to figure out where it came from. Okay, so I'm going to show you a couple of applications. One of them is hash tables, and the other has to do with hacking. Okay, so black hat, white hat, security sort of hacking. Okay, all right. First thing, hash tables. What's a hash table? A lot of you are familiar with trees as your dynamic data structure. You put something in the tree, and you sort of know where to find it based on sorted order, right? You go left, you go right, and each choice is like doing a binary search, basically. Those are really good for figuring out, doing comparisons, trying to figure out which, I don't know, if you want to search for all student ID numbers that are in a certain range, okay, that sort of thing. But if you don't need that, and often you don't need that, you can do something known as an indexing table. Okay, so it's basically a big array. So you can imagine, going to the student ID number situation, that everyone in here has a unique student ID number, right? That's why it's called your ID number. You can make an array and just plunk in your student, information, data, whatever your personal stuff is, in that slot in the table. Okay, so you just say array bracket your student ID number equals whatever record. You can look it up. Okay, that's order one access, right? Order one access. That's way faster than the log n access of a binary search tree, right? Red-black tree. Okay, so it's much faster. The problem is that your student ID number is 9 digits long, which is a billion, right? Your arrays are usually not a billion big. Okay, that would be a very big table. Okay, it would cost more memory than most of your computer systems have, right? And most of your numbers start with a 3, right? It would be very concentrated data for I don't know, 1 million of the entries, say, and most of the table would be empty. Okay, so to save memory, what they do is they hash the key, so the key being your student ID number. So they do some mathematics on the key. I mean, it could be your student ID number, it could be your name. Like if you imagine, how would you arrayify your name, right, into a table? You can't, right, because a string, there's an unbounded number of possibilities for a string, right? Okay, so, but anyway, back to the student ID number. Okay, so there's a billion entries in this table, but, basically there's only been about 1 million students in all time, and that's a few. Okay, so what do? You run your ID number through a hash function, and you map it onto a smaller range, a much more reasonable sized sort of table, so you save on memory. And then instead of going directly to the key, you go to h of key. Okay. Now, the problem with doing this is that if you ever have a conflict where you end up hashing to the same value, one of your pieces of data gets overwritten. Okay, and that's not a good thing. Okay, we would like our data to not be overwritten. This is known as a collision. Okay, so this is indeed very much like the birthday idea, right? You would like, ideally, to have an injective function, right, that it maps to something unique all the time, and that will give you order one lookup, which is awesome. Okay, or you would like to minimize that. Okay, so the way that hash tables resolve collisions is often with a linked list. You just pile them on top of a linked list and do a linear search, and hopefully there's not more than 1 or 2 things, maybe 3 things in the list for you to search, so it's not that slow to search. Okay, so that's how they resolve it. So how big does n need to get before it's likely to get a collision? Well, I don't know exactly. Well, I do know, and you know, because it's the same as the birthday thing that we did as a group, right? We want to find out what's the chances that there's any pair of hash indexes that match. Okay, so this is very much like the birthday part 1. Now, there is a hack that attacks hash tables that do something naive, and that is if your hash function is well known, like say it's part of some open source piece of code, then you can feed in indices into the hash table deliberately that all collide to the same value. And if that occurs, if everything sits in the same value, then it basically becomes a linked list, and doing linear search is really painful. Okay, so this gives you order n running time per search if all map to the same value. Okay, so all map to the same index, and this is known as a hash flooding attack. And it's done to slow down systems that you want to slow down. Like if you want to attack Microsoft Bing or something, it's got a weak algorithm there, you can do a denial of service attack on that. Okay, so the counter to that is randomize your hash function. Okay, so pick a randomized hash function at runtime, and then nobody can reasonably predict and attack your system that way. Okay, but this is a randomized data structure. Okay, so you apply randomization to the birthday thing to the data structure. Cool. Okay, the other one I want to show you has to do with hacking. And when we talk about crypto security, usually they talk about the CIA triad. This has nothing to do with the CIA in the United States. It refers to confidentiality, integrity, and availability, these 3 strands. There are two others as well that have been folded in, but these are the main three. Confidentiality, can only the authorized users access the info. This has to do with things like passwords and authorization. Integrity, is your data the right data? And availability, do you have reliable access to the information? Okay, so we're going to deal with a couple of cases here. One is integrity of downloaded apps. Okay, so when you download an app from the internet, especially on open source sites, they usually give you a key. Okay, so they give you like a MDA5 key. That's one of the most common ones. And you download this along with your software. You download it from a third party, and then you run a hash function on the piece of code you downloaded. Okay, so you can imagine the piece of code is a super huge long string, and it runs a hash function, some sort of math on it, and it gives you a result, a big binary string. Okay, where the digests are 256 bits long. Okay, so this is a very big target to shoot for. Okay, and if it happens that the download was corrupted, then you realize that you should install. Okay, so this is a safeguard to make sure that you're not installing bad software or malicious software as well. Okay, so if you put on the black hat, okay, and you want to hack the system, what do? Well, first you write a malicious piece of code that, say, steals credit card information or whatever it is, and then you append useless code, and you keep on doing this over and over and over again until you get the same digest. When you digest the same thing, until you get the same thing as the checksum or whatever it is for the app that is legit. Okay, and you keep on doing that. Okay, so you append some code, check, append some code, check, append some code, check, until you get lucky. Okay, and what's the chances that you get lucky? It's 1 in 2 to the 256. It's a really small number. Okay, 2 to the 256 is essentially the number of days in the calendar year that you're trying. So you're trying to find. You're like the person that's waiting for to find somebody who matches your birthday. Okay, so how long do you have to wait? You have to do roughly 70% of this number of iterations before you, and that's not. It's probably not reasonable to do. Okay, so this is a countermeasure for hackers that will post illegitimate code. Okay, so this is like birthday paradox 2. Incidentally, if this sounds familiar to you, it might be because of the way the blockchain works. Okay, so those that have server farms that are trying to mine crypto and this sort of thing, they're doing this exact same thing, but for a much smaller space. Usually, it's something like 2 to the 64. It does take a lot of iterations to find some checksum that works. Okay, that matches 64 binary digits, but that's indeed what they're doing as proof of work. Okay, so this also has applications to the blockchain as well. Okay, so you're trying to find a match. Okay, given what you're after, you're trying to find a match, and the only way you can do it is by go and test. Try something random and test. Okay, last is another type of hacking where it has to do with digital signatures. Okay, and in this scenario, there are two entities, Alice and Bob. These are pretty typical names, A and B. And Alice is going to try and trick Bob into signing away his life savings. Okay, and here's what happens. Alice creates a nice contract C. Okay, so a big string of stuff, and Bob would want to sign this contract. And there's a mean contract X. Okay, so something that says take your life savings, and Bob is signing that over to me. And they have to have the same checksum. Okay, they have to have the same hash value. Okay, so what does Alice do? Well, Alice creates little cosmetic variations in each of these two things and keeps on hashing these things until they get a pair that match in digest. Okay, so what's the procedure? Well, when you do digital signatures, you hand the contract to somebody, and then Bob will sign it by hashing their digest and appending it to the end. And Alice can take that digest and just append it onto the malicious contract, and then claim that Bob signed the malicious contract, okay, because the digests will match. Okay, so this is not exactly the same as birthday 1, okay, because there's a set of good contracts and a set of bad contracts. And we're looking for, we're sampling all these things over here, and we're looking for one that matches between the two. Okay, so it's not any pair. You can't actually take a pair that goes internally. Okay, so this is not allowed, and this is not allowed, because one of the contracts has got to be good and the other has got to be bad. Okay, but it's similar to birthday paradox 1. Similar in the math. Okay, you don't have to search as much. It sort of behaves like the square root. There's a hand that went up. Yeah, so Bob, in order to legitimize this thing, they have their own private key, okay, and they use that to sign their thing. And the way that they verify that it's Bob actually is that Bob's public key is known, so they just run it on the private key and it gives Bob's signature back. So that's how they verify that. So that's how they sign this thing in the end. So Bob has his own signature that legitimizes it. So yeah, but then Alice appends it to X, which is the bad one. Did I answer it? Yeah. Okay. Other questions? This digest stuff is pretty neat, and if you understand what the brute force characteristics are, especially of birthday 2, that will go a long way to explaining how the blockchain works if you haven't looked into that yet. So I highly recommend you go take a look for extra reading. Yeah. Okay. Let's go on to the next unit. Eh? Let's do it. Okay. Conditional probability. Adding extra information onto our probabilities. All right, so what's the story so far? The story so far in our probability adventure is not everything is uniform. Each outcome in a sample space is assigned a probability between 0 and 1 such that totals give you 1. Any subset of the sample space in event E, you can add up all the individual probabilities and get the probability of that event. And there are many probability rules. Okay, I don't want to review them now. We just sort of did a summary slide not too long ago. One of them that will arise again and again is the union bound, so I'm just going to re-mention that here. Okay, so for a bunch of events that don't have to be mutually exclusive at all, if they are, we'll get equality, but that's not what we're at here. Any collection of events, the probability of any one of those events happening is bounded above by this, the sum of their individual probabilities. Okay, so this is I'm sort of putting an asterisk beside that, but I will mention that this thing here, equality holds if all of these events are mutually exclusive. Okay, you just get the Kolmogorov axiom back, actually. Okay. And we saw a nice approximation at the end of last time, and a variation of that from calculus. One is that 1 plus x is pretty close to e to the x. When x is close to 0, we're going to use this over and over again. The other is this limit definition. This sort of comes from compound interest formula. If you take 1 plus 1 over 10 and raise it to the 10, what do you get? Well, maybe we'd do better if we took a little less interest and went over a few more years. Okay, so as this thing shrinks and this thing grows, it actually converges to e, and that's where e comes from. Okay, both of these approximations are we're going to use more, so keep them in mind. All right. First, a little background, and this is from, I believe, O'Donnell, one of the reference books. Okay, probability is about modeling reality with math, and there's nothing special about probability. Everything in problem solving is about modeling things with math. And the problem with this view is that there can be ambiguity. I give you a problem, and some of you go, "Is this selection with replacement, without replacement?" And you have to decide. Is it a permutation? What is it? What's the thing? Okay, so we as computer scientists have a sort of a nice advantage in that we can disambiguate things by using computer programs. Okay, and so we can write things down and model it using computer code. Okay, so we're going to add an extra step in here, okay, and map reality onto computer code. And there's no arguing about what a computer program is supposed to do. Okay, so it's basically math in algorithmic form, and then we can analyze that without any ambiguity as to what's going on. Okay, so translate that into math. Sure, we might disagree about what the computer code ought to be, but we can't argue about what the computer code is, okay, and what it means. Okay, so that's going to be our strategy, and in order for us to do randomization in computer code, we need a couple of functions. Okay, so the first function is Bernoulli, all right, and it has to do with flipping not just a fair coin, but a biased coin. Okay, so typically, say a person flips 2 coins, 10 coins, whatever it is. This is Bernoulli of a half, and heads is it returns a 1, and tails it returns a 0. Okay, so in general, we have a function called Bernoulli that takes a probability p between 0 and 1, and it will return a 1 with probability p. 1 represents heads, 0 represents tails. Now, we are going to stick with the 1-0 thing because it's much easier to add up a bunch of 1s together than add up a bunch of strings together. Okay, but if you really wanted strings, you could run this if statement, right? If coin is equal to 1, then it's heads, and if coin is equal to 0, then it's tails. We could do that if we wanted to, but we're going to try to stick to 0s and 1s, okay, because mathematically it's easier. Furthermore, subsequent calls, okay, so calls back to these randomized functions behave independently. And this is sort of how we expect fair coins and fair dice, even unfair coins and unfair dice to behave, that they have no memory. Okay, so calls to one do not affect future calls to the same thing. The second function, besides Bernoulli, is randint. Okay, and if we're talking about a standard die, randint, this would be randint 6. Okay, a 6-sided die for a standard die. But there's nothing magical about a 6-sided die, right? We could have a D10, a D20, a D100. We could have a D5 and a D13. We could do all sorts of crazy stuff. Okay, and randints will pick a number between 1 and m with probability 1 over m. Okay, so if two standard dice are rolled, we could take die 1 and die 2, and we will get two numbers between 1 and 6, and then do something with die 1 and die 2. All right, so we're going to write some computer code for a patient has a 1 in 10 chance of having a certain disease. Think about how you would write that. Yeah, think about it. Okay, so here's one possibility that you might have come up with. Say X gets randint of 10. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and in one of those possibilities, 1 in 10 chance they have the disease. So if, I don't know, X is equal to 1, that's pretty arbitrary which one we pick here, then disease equals true, otherwise disease equals false. Okay, this is not the only way we could have written this. Give me another way. Give me another way. Good. Okay, so disease equals Bernoulli 1/10. Okay, so with probability 0.1, okay, so this is an alternate version of that 5-line piece of code. Sorry, Bernoulli is 1 minus. It returns 1 with probability p, and 0 with probability 1 minus p. So here, if we just check this out, so 1 minus p would be 9/10. 9/10 of the time is going to give us 0, which I think matches what's over here, right? Are we good? You had your hand up. Was that to answer this one? Yeah. Okay. Good? Okay. Next. Probability trees. All right, first the problem. An ophthalmology patient has an 8% chance of being red-green colorblind, if male, or a 0.5% chance otherwise. Okay, so I don't know, there's a lot of males in the room. I'm one of them. I see the number 21, because I have some colorblindness. And maybe some of you do too. If you don't, you probably see the number 74, which I also see. I'm slightly red-green colorblind, sort of on the edge. Okay, but anyway, if you've never seen that before, now you know. And because it's sex-linked, it's with the X chromosome, and the Y chromosome doesn't sort of match the X off. And it's a recessive gene. Non-males are less likely to be there. And I know what world I'm living in. Okay, I know life is more complicated than male and female. Okay, I don't want to bring too much complication into these problems. Okay, so apologies, but we're just going to deal with it like it's that way. Okay, so sorry. We can model this using computer code, same as the previous thing, but with 2 strands. Okay, one being male, and one being colorblind, but with an if statement. Okay, so we'll have an if statement depending, and there'll be 2 different calls depending on whether it's male or not. Okay, so is male is a Bernoulli of a half. I know that's not exactly true either, but it's pretty close for our purposes. Again, I don't want to get too complicated about this. And if is male, then we'll call Bernoulli on 8%. Okay, so is colorblind will be Bernoulli 0.08. Otherwise, is colorblind will be Bernoulli of 0.5%, so 0.005. Okay, so we're going to be branching into the realm of probability trees, and I sort of gave you a bit of a crash course drawing those things out, right? We have the multiplicative rule. It's a good way of organizing yourself. One of your texts has a systematic method of dealing with probability problems like this, and one of the steps is draw a probability tree, and then there's a couple other steps about analyzing that probability tree. And if you're lost or you're feeling lost about a problem, I highly recommend following those steps. Okay, you're less likely to get lost in the problem, and some of these things are confusing. Okay, so I admit that it can get a little confusing, a little bit woolly. Okay, we have a few new definitions and some old ones. Okay, first one. An experiment is a block of randomized code. We're now talking about a block of randomized code, and that randomized code will translate into a probability tree. Okay, so how does a probability tree work? Each randomized step in the algorithm will generate a branch. So the initial thing is a coin toss, where it's 50-50 between male and not male. And you write on the branches the probability such that they all sum to 1. Okay, if male, then we toss another coin, and that coin will be 0.08 on one direction and 0.92 on the other direction. Okay, signifying colorblind or not colorblind. And we could label these things like this: male not colorblind, male colorblind. And a different coin will be tossed if female, female not colorblind, female colorblind. Okay, so 0.5% for colorblind, 0.995 for not. And you'll notice that everything sums to 1. Here there's sum for 1, that sums to 1, that sums to 1. Okay, I'll come back to this, I promise. It's not going away, it's not going far. Okay, I want to get these couple definitions done and then we'll call it a day, okay? So, definition, outcome. Okay, so outcome is the result of an experiment, okay? In this new definition, we had a new definition of experiment. Okay, an outcome is any leaf in the probability tree. Okay, so any leaf in the probability tree represents the state. So there are 4 leaves here. They all happen to be on the same level, but it doesn't have to be that way. Okay, they can be on, they can all be on different levels, actually. And we'll see some experiments where that's the case. Okay, so the outcomes are all the leaves of the tree. The sample space is a collection of all the outcomes. So it's a collection of all the leaves of the tree. Okay, so that's the same as it was before. And an event is any subset of those outcomes. Okay, again, just a collection of leaves in this case. The probability, this one's new, of an outcome, and I showed you the punchline a week ago, right, when we talked about probability trees before. It's the product of the probabilities along the path to S. Okay, so if we were to multiply each of these things going down the tree, we would get their individual probabilities. And I don't have time to do that right now, but we will do an example with this on Friday. Okay, so we will multiply these together, but this outcome will be a half times 0.995. This will be a half times 0.5%. This will be a half times 0.92 and a half times 0.8. Okay, so those things multiply. Therefore, the probability of each outcome is greater than or equal to 0, and the probability is actually strict. And the reason is that we tend not to draw branches where the probability is 0. We just don't include them in the tree. Okay, so this is actually strict inequality, because we tend not to draw branches with 0 probability. And if we want an event, want to look at its probability, we just add up all the probabilities for each of those outcomes. That's the same as it was before. Okay, so this is probabilities as it's associated to computer code and probability trees. Does the improbability, all of it sum up to 1? It better. Okay, so this thing ought to hold. And the reason that it should hold is sort of by induction, right? If you were to add everything up, bottom up, right? Everything here is 100. Everything here is 100. So by induction, you sort of, or even top down, everything is split up into its, left and right, and all of its subtrees will add up to 100 in some sort of, nested bracket situation. Okay, so yeah, the intuition is that it should add up to 100, and that's a good thing because we want